Here we go. This chapter 11 problem. We've got a stove with a burner thermal power rating of 1.2 times 10 to the 4 BTU per hour. Oh. We place a 0.353 kilogram aluminum pot containing 2.5 liters of water at 20 degrees Celsius on the burner. We're going to assume atmospheric pressure of 1 atmosphere. First thing is it's asking for a couple conversions. We want to convert 1.2 times 10 to the 10 to the 4 BTU per hour to joules per second, because we don't want BTU per hour, we want joules per second. So what do we do? This one's easy. 1.2 times 10 to the 4 BTU per hour. We look up the conversion. I think it might even be on the equation sheet. There are 1,055 joules per BTU, and in 1 hour there are 3,600 seconds. And then we find that it's 3,517 joules per second. That's a 7. This should be old hat. Right? This should be automatic for you guys. Calculate the mass in kilograms of 2.5 liters of water. I can tell you right now it's 2.5 kilograms. That's the way it works. But let's go ahead and do it. Actually, so remember that the equation, we've got, what do we have? We've got the volume. We have the volume of water. We want to know the mass of that water. So we need the density. We need a density equation, because you need to know the density of whatever it is. If you have the volume and you try to get mass, you need to know the density. So there it is. Density is mass over volume. That means that mass is density times volume. The density of water, we can look this up, or you can just remember it, is 1 times 10 to the 3 kilograms per meter cubed. That's why I was doing it down there. I need a room. Kilograms per meter cube. And then our volume is what? Oh, it's 2.5. Oh, I don't have enough room. 2.5 liters, and then what? And then what? Well, again, it's on the equation sheet. 1 liter is 1 times 10 to the minus 3 cubic meters. 1 times 10 to the minus 3 cubic meters is 1 liter. Seems like there could be a rhyme there to remember that. But basically, what is on the equation sheet? Let's just look at the equation sheet. Here it is. Yeah. So what happened to my? That's so frustrating. 1 cubic meter is 1,000 liters. That means that 1 liter is 1 times 10 to the minus 3 cubic meters. Okay. So what we find is that the mass is 2.5 kilograms. 2.5 liters of water has a mass of 2.5 kilograms. You can just remember that. You can just remember 1 liter of water has a mass of 1 kilogram. That's assuming temperature and all that stuff is at 4 degrees Celsius and all that stuff. But it's close even if it's not, and it is. So don't worry about it. I guess we're told, what is it? We're told it's 20 degrees. 2.5 at 20 degrees. It's close enough. Okay. Calculate Q boil, the amount of thermal energy required to bring the water to a boil. What? Okay, so we've got water at 20 degrees Celsius, and we're just bringing it up to 100 degrees Celsius. So, this is, yeah, we've got to go to our old friend. Actually, it's a combination of our old friends. We've got, well, because we're not in an isolated system, the amount of heat is the sum of all of our heat. So it's the heat of the aluminum pot, right? It's an aluminum pot, yeah. Plus Q of the water. And how do we get those Q's? We get those Q's with our Q equals MC delta T. Okay, so our total heat is the mass of the aluminum times the specific heat of the aluminum times the change in temperature of the system. Well, it's yeah, it's going to be T. It's because they start at the same temperature, right? So both things are at the same temperature. So we actually can kind of factor, well, let's just leave it in there. We'll just say delta T. That's what we'll say, MC delta T. And then plus M of water, C of water, delta T. And this is what I was rambling about. We can actually factor out that delta T from both terms, so we end up with MAL, CAL, plus MW, CW times delta T. I think we have everything, or we can look up everything. So the amount of heat, this is to boil, is the mass of the aluminum. What was the mass of the aluminum? 0.353. We can look up the specific heat of aluminum. 900 joules per kilogram degrees Celsius, plus the mass of the water. What is the mass of the water? Why can't I remember any of this stuff? 2.5 kilograms. Specific heat of water is 4186. Oh. Joules per kilogram degrees Celsius. And then our change in temperature, our final temperature is 100 degrees because we're trying to bring it to a boil. Water boils at 100 degrees minus our initial temperature, which is 20 degrees. It's a lot of stuff. It's just a lot of buttons on your calculator, though. You can get that done. That looks pretty good. Okay, calculate T boil, the time required to bring the water to a boil. Oh, did I do that in the wrong place? Oh no, that's, I calculated the amount of thermal energy to bring it. Now we're trying to find the amount of time to bring the water to a boil. Okay, so remember, V equals Q over time. It's on the equation sheet. So that means that the time to boil is Q over P. Q boil over P. Power. Where are we going to get the power? We know what the power is. Yeah, we know what the power is because we're told it's 1.2 times 10 to the 4 BTU per hour, and we actually converted that to joules per second, which is what we need. So here's what you're going to do. You're going to take your result from part C, and you're going to put it here, and then you're going to divide that by whatever we got in part A, 3517 joules per second. Is that what I said here? Yeah, 3517 joules per second. And that's it. That's the time it takes to boil. Now calculate T evaporate, the time required for all the water to evaporate once the boiling has begun. So I'm not going to work this whole problem, but it's very much like parts of all the other stuff. So the time is going to be the heat to evaporate over the power, which is the same. It's that value right there because it's the same stovetop. What is the heat required to evaporate? Well, in this case, we are undergoing phase change. So we aren't using our old friend Q equals MC delta T. We are instead using our very simple equation, our latent heat equation, right there. Q equals M times L, where L is the latent heat of either fusion or vapor, vaporization, and it's going to be vaporization. So it's MLV. So it's the mass of the water and the heat of vaporization of water. So that'll get you that value. You already have that value. You put it in your calculator and you're good to go. Okay. That ought to do it. There's a lot going on there, and part E was like 3 problems wrapped in one, but still easy. You have to admit it's still easy. Okay, let me know if you have any problems later.